In this programming tutorial, I'm going to break down the Leetcode problem longest substring without repeating characters, also known as longest unique substring. It's a tricky problem that appears in many coding interviews. As usual, I'll start with the problem description, the brute force solution, the conceptual overview of the optimal algorithm, estimate the runtime and memory complexity, and eventually we'll arrive to the coding implementation in JavaScript and Python. The task description goes like this. Given a string s, find the length of the longest substring without repeating characters. And whenever the task is about counting something unique, you should immediately start thinking about a set as your primary data structure for the task. Let's look at the examples and try to solve them in our heads. So for the first string, the expected output would be 3 because the longest unique substring would be ABC or BCA. In the second instance, the longest substring without repeating characters would be just a single character B, so the output would be 1. And in the third example, the answer would be 3 because the longest substring without repeating characters would be WKE. Let's use the first example to see how we can use a set to engineer a brute force solution. So we'll start with the first character of the string. We'll put it into a set and move on. Then in the second character, we'll check whether this character is in the set or whether it's not there. It's not there, so we're putting it in. For the third character, once again, check, put in if it's not there. For the fourth character, do the same. Realize that A is already in the set, so we can't put it in anymore. And here we will stop and record 3 as our current max for the first unique substring. Max is equal to 3 at this point. Then we'll start from the second character of the original string. We'll do it the same way. We'll put it into the set, then move on, put the second character into the set, then the next one, and then we'll realize that actually B is already in the set. So we can't expand the set anymore. We can't expand the substring anymore. We check the size of the set. It's still 3, so the max remains at 3. We cannot update it here. We continue doing this. We continue following the same approach, starting with the next character of the original string. So it will be C, A, B, and then we realize that the next one would be C, which is already in the set, so the max remains at 3. And so on and so forth, we move on, and eventually we'll arrive to the end of the string, having passed through all the unique substrings of that original string. Such a brute force solution approach has the runtime complexity of O(n) squared and space complexity of O(n). The O(n) squared comes from the nested loop, and the O(n) comes from the set. Even though it's not an optimal algorithm, it's a good starting point to understand the optimal solution. Let's implement it in JavaScript to make sure it works. So here we're going to need a variable to hold the max, and then a set to keep track of the characters that we use for our substrings. Then we write a standard nested loop from I equal to 0, I less than s length, I plus plus. The second loop for j equal to I, j less than s length, j plus plus. And the first thing to do here is to check if the set has the current character, s char at j. And it happens to be the case. We check if we need to update the max by doing if j minus I is greater than max. We set max equal to j minus I. Alternatively, this could be the size of the set, and we'll break the loop. If the current character is not yet in the set, we'll put it in there. We'll say set add s char at j. Then there's a corner case. If we happen to run to the very end of the string in our internal loop, and we haven't yet found any duplicates, we would not update, we would not get into this branch, and we will not have a chance to update the max. So here we need to add another if that says if j is equal to s length minus 1 and j minus I is greater than or equal to max. In this case, we need to update the max to j minus I plus 1. 1 goes for the current character because it would be in the substring as well. And as soon as we end the inner loop, we'll need to clear the set with set.clear. And eventually, when we're done, we return the max. Return max. Let's run the code to verify that it works. It does work. It was accepted. So let's try to submit it to see whether it will pass the performance test. Its runtime is pretty bad. It beats just 20% of all solutions, but you see that it's perfectly okay from the correctness standpoint, but not from the performance standpoint. Let's go back to the drawing board and see how we can improve the algorithm to get to a linear runtime. An optimized solution is based on an algorithm that's called a sliding window. Just like we did in the beginning of the brute force solution, we'll try to expand the unique substring as long as we can, starting from the first character of the string s. As soon as we run into a character that's already in a set, we'll shrink the sliding window by removing the leftmost character of the original string from it. We'll keep removing characters until the substring becomes unique. Let's see how we can conceptually apply the algorithm of the sliding window to the first string. We start by taking a look at the first character, by putting it into the set. Then we expand the sliding window. We go to the second character. We put it into the set as well. All good this far, no duplicates. Then we move on to the third character. We put it into the set as well. No duplicates. And when we get to the fourth character, we find a duplicate. So before we add it into the set, we need to remove the characters from the set, starting from the leftmost one. So we remove this one from the set and check whether the current element, this A, is in the set or it's not. It's not there anymore, so we can add it. And on each iteration, we check whether the current size of the set is greater than the current max. If it is, we update the max. Then we move on. We get to B. B was in the set as well, so we remove it. And actually here, we don't remove the B itself. We always remove the leftmost character until the current one is not in the set anymore. Next character, C, also in the set, so we need to remove the leftmost one, add this one, then B. We see that here B is in the set as well. So we go, here it will be evident. We go from the leftmost element, which is in this case A, remove A, and then we check again whether the B is in the set. Yes, the B is in the set, so we remove another one. We remove B. Is B in the set? No, it's not in the set. So now we can add it. We add it, and now our set is C and B. And here, when we arrive to the end of the string, it's another B. We keep following up. We remove C, then we remove B. The set becomes empty, and now we can add B. Eventually, we got to the same result of 3, because the maximum size of the set during all these operations was 3. Now let's go back to coding and see how we can modify the solution, or how we can rewrite the brute force solution to get to the linear time sliding window. Let's go from the first line. So we still need a variable to hold the max, still need the set, but now we'll need an extra variable. We will need to keep track of the leftmost element. So we'll say let left equals 0. We still need the outer loop, but now we don't really need this inner loop. We need it, but it will be very different from what we have used in the brute force approach. We don't need to clear this set as well. We'll be just removing items one by one. So the first thing to do here is to write a while loop that will loop until the set has the current element as char at I. And if it's in there indeed, we'll say set delete s character at left, and increase the left pointer by doing left plus plus. When we're done with this loop, we're absolutely sure that there is no duplicates in the set, that there are never any duplicates in the set, of course, but that the current element, when added to the set, will not, now I would say it differently. So after this loop, we're sure that the current character of the string s is not in the set. So it will expand the substring. So we can safely say set add s character at I. And then we can update the max by saying max equals math max, set size, or max. This way, if the size of the set is greater than max, we'll update the max. And of course, eventually we return the max. Let's run the code. It was accepted, all the test cases are green. And now let's submit to see whether our runtime improves. The runtime improved. Now we beat 93% of users with JavaScript, which comes from the improved computational complexity of ON, linear complexity. Our algorithm still takes ON space because we're using a set that can grow up to the whole length of the string s. Let's try to do the same thing in Python. So in Python, we follow the same route. We create our variables, max equal to 0. Oops, we don't need a semicolon here. Max equals 0, left equal to 0 as well. And we'll have some storage as our set. Then we'll have a loop. We'll say for character c in string s. Then we run a while loop. It says while character c is in the storage. Oops, made a mistake here in storage. We'll remove it from there, saying storage dot remove s left, and we'll advance the left pointer, left plus 1. Then once we're sure that the current character is not in the set anymore, it's not in the storage, we'll say storage dot add c, and we'll update the max if needed. If len of storage greater than max, we update the max. We say max equals len of storage, and eventually return the max. Run it, all green, accepted, and submit the solution. The runtime is 47 milliseconds, 16 megabytes of memory. We beat 97% of users with Python 3, and we beat 82% of users on the memory side, which is a great result, which clearly comes from the linear time and memory complexity of our algorithm. That was it. I hope you found it helpful. Let me know what you think. Thanks.